Welcome. Welcome to video number 5 of module number 6, which is on traffic assignment. And the topic of this particular video is going to be just to get you some ideas about capacity constraint, also known as capacity restraint. So it goes by that name as well. Actually, in this presentation itself, I interchangeably use both words. Why capacity constraint? If you saw the videos before, all or nothing or stochastic, I barely mentioned anything about capacity, the volume. So travel time is a function of traffic volume, correct? So what good is in any assignment technique if it doesn't consider that travel time and flow relationship? That is why as the travel time increases, I'm sorry, as the volume increases, travel time increases. So we have to take that into consideration. So essentially, flow to capacity ratio is what we are looking at. All or nothing assignment, that's why it's such a goofy technique. Almost nobody uses, but there are situations where you could use it. So capacity restraint can be worked into stochastic assignment, which we just talked about in video number 4 of traffic assignment of module 6. But it gets already that is complicated. It gets even more complicated when you include capacity restraint. So what is the speed versus flow relationship? So this is the flow. If you've forgotten, Q represents flow, which is vehicles per hour, and U being the speed, let's say miles per hour, mph. So this is the simplest. You can see as the flow increases, speed goes down. If only it is that simple. But if it is like this, how is it going to relate? How is it going to relate to travel time? Remember, in pathfinding, we are not looking at speed, we are looking at travel time. Speed has to be converted into travel time. So let's take a look at if this were your speed flow relationship, how does the travel time flow relationship look like? It looks like this. If your speed flow relationship is like that, your travel time to traffic flow, which is Q here, represents is like this. You have this being your free flow travel time. All right, so far so good. But when we learned about models of traffic flow, so this is in your intro course to transportation engineering. So we know there is something like this. It's a parabolic relationship between speed and flow, and somewhere here is your capacity, which is Q capacity. Sort of like here is free flow speed. Remember that? It's coming back. Okay, this is more or less a very realistic speed versus flow relationship. And a corresponding travel time versus flow relationship will look something like this. It's a power of volume capacity ratio, which we will see what that is. Again, here is your free flow travel time. And if your capacity estimation is correct, this should go somewhere asymptotic to capacity line, but it never is accurate. I mean, capacity is just a belief, it's not reality, so it's never going to be accurate. So you will see, that's why you see volume capacity ratio exceeding 1. If your capacity estimation is so correct, how can volume exceed capacity, right? But in practicality, you'll see volume capacity ratio is more than 1 because your capacity estimation is wacko. That brings us to introduction of the term capacity restraint. Now, we just said volume delay relationship, or it's actually volume versus travel time relationship. Travel speed decreases with increase in flow, which travel time increases as the volume capacity ratio on the link increases. So, way back when Federal Highways Administration was not there, actually, there is a Bureau of Public Roads, and before the Department of Transportation was formed, Bureau of Public Roads is the one that was in charge of highways at that time. I believe this is in early 60s. They came up with this a function formula. Travel time on a link is a function of free flow travel time and volume capacity ratio. So that is in its entirety. This, what you see here, ladies and gentlemen, this is your BPR function. So how does it look in terms of uh, in a chart? So here you have the free flow travel time, and it goes pretty much parallel to x-axis to some extent, even if a volume capacity ratio is up to maybe 7.765, something like that. And then the travel time keeps going up and up and up like that. In this case, you see a travel volume capacity ratio even 2. So this is the relationship they propose that should be used in capacity restraint assignment. In other words, when you put more volume on a particular link and you have to reduce its travel time. So now here is a catch 22. Travel time is dependent on volume capacity ratio or volume, essentially capacity assuming it's constant. Travel time dependent on volume, and volume is dependent on travel time. So that's why this whole thing is an iterative process. So you will do it like a few number of iterations and then do some sort of a reconciliation process or averaging or some other mechanism by which you bring down an estimate of traffic on each of the highway links you are modeling. Let's take a further look at this BPR function. If you put that in the previous form where t equals t sub 0 1 plus alpha v over c b, if you put in the alpha place 0.15, in the beta place 4, that is your BPR function. But this is a generic form of BPR function. If alpha value is 1 and beta is 4, at volume capacity ratio 1, your travel time is going to be twice that of T0, free flow travel time. Remember, T is a function of free flow travel time and volume capacity ratio, alpha and beta being constant. If the volume capacity ratio is 0, that means there's no traffic on the highway. Your travel time is nothing but free flow travel time, which is T0. And if you exactly at half that volume capacity ratio, travel time barely changes, only 6% higher than T sub 0. That's when alpha is 1 and beta is 4. And that is for a level of service. These two values I just mentioned, alpha 1 and beta 4, they correspond to a level of service of E. And if you want to use level of service D as your criteria, use 0.15 for alpha. And that's the BPR function. This is the easiest of all the travel time functions. And believe me, bazillion research papers are there on this travel time functions. You will see some of them right now. Here's one, travel speeds. So remember, if you want to plot speeds versus flow, the typical shape of the curve here is U, here is Q. Typical shape of the curve is it should look like this. So here you have U, here U, and here you have VC ratio. Well, basically Q or VC ratio, your curve should be in the same form. I think this is probably the one that is in the closest form. So this is the old BPR curve, what I just circled there. You have highway capacity manual for 70 miles per hour, highway capacity manual equation for 60 miles per hour, highway capacity manual 50 miles per hour. There are different functions, and again BPR coefficients, recommended coefficients for multi-lane highways and freeways, they are like that. Who gives that? NCHRP 365. That's your textbook. Now here is another fancy um, link performance function. Oh, that's another name too. Travel time flow relationship, or travel time to VC relationship is also called link performance function. So you might want to do that somewhere. Link performance function. Performance function. So this is used by Virginia Travel Demand Modeling Policies and Procedures Manual. That's what it says. For freeways, they use alpha of 0.20, beta of 10. So for non-freeways, alpha of 0.05 and beta of again 10. So these are some of the link performance functions. We'll be using standard one in our problems, which we will start seeing from video number 6, which is the next one. So this will conclude our video number 5 of module number 6. See ya.